and any set S subset of Rm, R to the power m, with volume of S bigger than the determinant of L. There are 2 points Z1 and Z2 in S, such that Z1 minus Z2 is in L. Okay, so quite a mouthful, but let's see what this means. Okay, so you have a lattice. Okay, any lattice, and let's pick a set S. Okay, any set you want, like any set you want. Let's look at this particularly ugly set. Okay, so this is the set of points in Rm. This is the origin. Okay, it doesn't matter where the set is. It could be any set in the space. The only condition is that the volume of this set is bigger than the determinant of the lattice. Determinant of the lattice is the area of this parallelogram, right? The volume of this set is bigger than the determinant of the lattice. What this says is that there are 2 points in this set S whose difference is in the lattice. Okay, so can I find an example? So I should be able to find an example of 2 points in the set, right? So can I do that? Well, yes, I can actually find many examples. Take this point here and this point here, which is actually this point shifted by the basis vector. Okay, if I subtract the 2 points, this is Z1, this is Z2. If I subtract the 2 points, I get this lattice vector. Okay? What this says is that in general this is true. This is not an artifact of the example. It's true. The proof, in one word, it's pigeonhole principle. Okay, you have 2 sets. One is bigger than the other. There have to be 2 points in the first set that map to the same point in the second set. Okay, so that's the idea. Let's see how the proof goes. A bit more formally. Okay, so proof. Okay, so the first thing I'm going to do is so this set is ugly, right? I mean, I don't want to deal with the set. What I'm going to do is I'm going to cut and paste. Okay, so let me use different colors. Okay, so I'm going to sort of transfer the part of the set which lies outside the parallelepiped, shift it onto the parallelepiped. Okay, so that's what I'm going to do. So let's say this part of the set shifted over to the other side. I will run out of colors very soon. This is this part of the set shifted over to the other side, and I can do the same thing with this also. Okay. So I can do this. Okay, so algebraically, formally, what's happening here is that I'm going to write S as a union of S sub V. Right? S sub V is the part of S that lies in a particular shift of the parallelepiped. Okay, so this is in fact what I would call S sub minus -1, 1. This is the part of S shifted by 2, 0. So this is S sub 2, 0, and this is S sub minus 2, 0. Okay, so I can write it down as a union of S sub V's for many V's. Okay, so what I'm going to show is the following. Assume that I take 2 of these areas, S sub V1 minus V1 and S sub V2 minus V2. Okay, so it could be this area shifted over by V1, or this area shifted over by V2. Assume that these 2 guys have an intersection point. Okay? The intersection is non-empty. Assume that there's a point that's common in between. Now I claim I'm done. Right? Why is that the case? Assume that Z is in the intersection of these two sets, these two shifted sets S. Then, well, this means that Z plus V1, let me call it Z1, right, is in S sub V1, therefore it's in S. And Z2 equals Z plus V2 is also in S. Right? There's an intersection point, and therefore there are 2 points, one in the first shift and the other one in the second shift. Okay? And now I'm done. Because if I look at Z1 minus Z2, what I get is V1 minus V2, which is the lattice point. Okay? So I got 2 points, Z1 and Z2 in S, whose difference is a lattice point. Okay? So once the intersection between 2 shifts of the S's is non-empty, I'm actually done. So the only thing I need to prove is that this has to be the case. Okay? Let me just tell you the intuition and leave the formality, the formal notation and so forth aside. Let me tell you the intuition for why this should be the case. Okay? Assume that no 2 no 2 shifts of the S intersect. I mean, all of them are, every pair of them are disjoint. Okay? Assume that that's the case. Then, the volume of S is equal to the volume of, is equal to the sum of the volume of the SIs S sub Vi minus Vi. Right? Volume of S is the volume, the sum of the volumes of SIs, but this is the same as the sum of volumes of, let me tell you what I'm doing here. S is simply a union of disjoint sets S sub V1, S sub V2, and so forth. Okay? So its volume is simply the sum of the volumes of all these sets. Now what I did was I took each of these regions, this is S sub V1, and I shifted it over by a particular lattice vector. Okay? So I didn't change its volume at all. The volume of S sub Vi is the same as the volume of S sub Vi minus Vi. Okay? So I didn't change the volume at all. Now I'm assuming that no 2 of these sets intersect. Okay? If these 2 sets intersected, then I'm done, right? So by contradiction, assume that no 2 sets intersect. So then this is the same as the volume of the union of S sub Vi minus Vi. Okay? Because they are pairwise disjoint. You have a bunch of sets. They are pairwise disjoint. So the sum of the volumes is equal to the volume of the union. Okay? Now, this set, the union of each of the sets S sub Vi minus Vi, is contained within the parallelepiped, because what I did was I shifted each of them to lie within the parallelepiped. So this guy is at most the determinant of the lattice. Okay? But now we have a contradiction. Because what I got is that the volume of S is at most the determinant of L, whereas that's really not the case. I assumed the volume of S is bigger than the determinant of L. Okay, so you have, so there you have a contradiction. So it must be the case that 2 of these sets intersect in a point, in which case I have, I have my 2 points. There must be. Okay. Good. Okay. All right. So again, it's a very intuitive theorem. It's just an application of pigeonhole principle, obfuscated application of pigeonhole principle. And then this is what it says. Okay, so this is the first step in the proof of Minkowski's theorem. time do I have? Okay, no, I'm on track. Okay. So given this, our second step is another theorem due to the same great person, Minkowski's convex body theorem. Which says the following: for any lambda cell and any convex centrally symmetric, which I'll describe what it is, define what it is, set S, there is a non-zero lattice point in S. Okay, so what it says is, okay, so let me describe what convex and centrally symmetric are. Okay, so this is the two-dimensional plane. A convex set, this is a convex set. Okay, this is a convex set, but this is not a convex set. What does that mean? A convex set is one where for every 2 points x1 and x2 in the set, alpha x1 plus 1 minus alpha x2 is also in the set, where alpha is in 0, 1. Okay? So in other words, if you take any 2 points in the set, all the points, so what does this give you? Alpha times x1 plus 1 minus alpha times x2 is all the points in the line between x1 and x2. Okay? All such points are also in the S. Okay, good. This is convex because if I take any 2 points, draw a line, all these points are also in the set. This is not convex because if I take this point and draw a line, these points are not in the set. Okay, so this is not convex. Okay, so that is convex. What does centrally symmetric mean? It simply means that for every point x in S, minus x is also in S. Okay, if I take the mirror image of x along this axis, that's also in the set. Okay, so what the theorem says is that for every convex centrally symmetric S, something I forgot here, such that the volume of S is bigger than 2 to the m times the determinant of L. Right? Because I can have a set with a very sort of tiny volume, which obviously doesn't contain any lattice point. So it has to have a lower bound on its volume, which is 2 to the m times the determinant of L. There is a non-zero lattice point. Okay, so this is the convex body theorem. And before I get to the proof, let me quickly tell you why the convex body theorem implies the Minkowski theorem. Okay, implies Minkowski. Theorem. If you think of the set S as the ball of radius r, the L2 ball, right? So which is just this, of radius r, with center at the origin. It is convex, right? Obviously, it's centrally symmetric, obviously. If I take a ball of a sufficiently large radius, then it contains a non-zero lattice point. How large do I need to take this ball to be? Well, the volume, I need to take R to be large enough so that the volume of the ball is at least 2 to the m times the determinant of L. Okay. Now, the volume of sort of a sphere in dimensions, there are expressions for it, there are sort of nice, tight expressions for this volume. Let me just use sort of an upper bound, right? So, volume of a ball, this is at least 2R over root m to the m. Okay, so this is something that you can compute. Never mind. Maybe I'll tell you in a minute. But the volume of an m-dimensional ball, you can bound it by this quantity. Okay, it's really r to the m, but there is a sort of a fudge factor, which becomes larger and larger as the dimension increases. Okay, so now we're in shape. Okay, so if 2r divided by root m to the m is bigger than 2 to the m times determinant of L, actually this is strictly bigger than, then we are in business. Then it means that this ball contains a lattice point. Okay, let's just calculate this. This comes out to r bigger than square root m times the determinant of lattice to the power 1 over m. Okay, if I take a ball to be larger than this quantity, then it will have a non-zero lattice point. In other words, the shortest vector of the lattice has length at most masses. Okay. So once I prove the convex body theorem, I'm in shape. It's a very general theorem that talks about any sort of convex centrally symmetric set. I'm going to instantiate it with a particular convex centrally symmetric set, namely the sort of the ball of a certain radius, and I get Minkowski's theorem. Okay, so in the 4 minutes I have left, let me try to, what should I try to do? Let me sort of skip the proof of the convex body theorem, okay, unless someone really wants to hear it. What's the verdict? What I want to tell you about is a couple of applications of Minkowski's theorem and some generalizations. So maybe I can state the theorem and I can leave the proof out so that I can put up the lecture notes. And, is that good? Okay, so what is important? The proof is important, but what is important if you sort of go out of here is the statement of the theorem. Minkowski's theorem states that there is an upper bound on the length of the short spectrum. That's it. Okay. In fact, let me erase this. Generalization. Like I said before, Minkowski's theorem is very non-tight. In fact, there are lattices for which have very, very short vectors, and yet Minkowski's theorem says that they have gives a very lousy upper bound. Okay? There is a sort of a generalization of Minkowski's theorem which is actually better in handling these difficulties, which says that not only is bound. Not only is the shortest vector smaller than this number, the geometric mean of the m shortest vectors is also smaller than this bound. Okay? So this number is actually larger than lambda 1 in general, but that is also shorter than this bound. So this is a sort of tightening, sort of generalization of Minkowski's theorem, which gives you a tight bound on the product of the lengths of the shortest vectors. Okay, so that's a generalization. I want to tell you about an application, Minkowski's theorem, and that's the last item on the agenda. An application to proving that the following theorem. This theorem has nothing to do with computer science, nothing to do with cryptography. It's a sort of pure sort of number theory statement, but it tells you how powerful lattices can be. Shows you a powerful application, surprising application of lattices in number theory. Okay, so this says, let P be a prime. So it's sort of a two squares theorem. Maybe it's sort of a stepping stone to Lagrange's four squares theorem. Okay, so what it says, let P be a prime, which is 1 mod 4. then P can be written, then there exist A and B such that P equals A squared plus B squared. Okay. Any prime which is 1 mod 4 can be written as a sum of 2 squares. Okay, that's what it says. How do you prove it? Well, okay, consider ZP star, Z mod PZ star, right? And since P equals 1 mod 4, minus 1 is a quadratic residue in this in Z mod PC star. Okay, so in other words, I'll tell you. Okay, so how do you tell if a number A is a slight detour? How do I tell if a number A is a quadratic residue? You simply compute A to the power P minus 1 over 2. This is either 1 or minus 1. 1 implies this is a quadratic residue. Minus 1 implies not a quadratic residue. Okay? This is a very sort of simple way to tell if a number is a quadratic residue. Is it square or not? Mod P. Now, in our case, P minus 1 divided by P minus 1 is divisible by 4. So P minus 1 divided by 2 is even, which says that minus 1 to the P minus 1 over 2 equals 1. So it's a quadratic residue. It's very simple. So what this means is that there exists a number I such that I squared equal to minus 1 mod P. Right? It's a square, therefore there is a square root which is I. Okay, so far, all sort of standard number theory, no surprises. The first, so the non-deterministic step of the proof is to consider the lattice generated by the basis, which is 1i, 0p. Okay, so this is one basis vector, 1 comma I, and you have 0 comma p. That's the other basis vector. Why? Heaven knows. You'll see in a minute. Right? So what can we say about this lattice? What can we say about this lattice? Let's apply Minkowski's theorem, right? We just saw Minkowski's theorem. So all you have to apply it somewhere, right? Let's apply Minkowski's theorem, right? So what does the Minkowski's theorem say? The shortest vector, I mean, this is bigger than 0, right? Certainly it's non-zero vector, so its length is bigger than 0. And Minkowski's theorem says that it's at most square root 2, square root m times the determinant to the 1/2. What is the determinant of this lattice? It's just p, right? So this is square root of 2 times p. Square root 2 times square root p. Okay, so number 1. Okay, so what is the? So let's look at this vector. Okay, the shortest vector of the lattice. We can write it as b times x1 x2. Right. So this is 1 0 I p times x1 x2, which is x1 I x1 plus p x2. Okay, I didn't do anything. I just said, this is the shortest vector. I just rewrite it as okay. What is the length of this vector? Well, so this means that 0 less than lambda 1 of b squared is less than 2 times b. Right? So this is just squaring. So what does this mean? This means that 0 is less than x1 squared plus ix1 plus px2 squared is less than 2 times b. I just took this vector, computed the square of its length. Okay? So my a is going to be x1. Remember, my goal is to write p as a squared plus b squared. My a is going to be x1. My b is going to be I times x1 plus b times x2. Okay. What do I know now about a and b? I know that 0 is less than a squared plus b squared. It's less than 2 times b. That's what I know. Now, if I prove that a squared plus b squared is 0 mod p, I'm done. Right? Because it cannot be 0, it cannot be 2 times p. It has to be p. Right? So, why is that true? Let's look at a squared plus b squared. A squared plus b squared. x1 squared plus I squared x1 squared plus 2p I x1 x2. Regular stuff, right? I'm not doing anything complicated here. It's this. I'm just expanding this expression. Now, mod p, this goes away because it's a multiple of p. This also goes away because it's a multiple of p. What is this? I squared. Now, we're going to use the fact that I squared equals minus 1 mod p. Okay, so this is x1 squared plus minus 1 times x1 squared mod p, which is 0, 1. Okay, so I just got two numbers, a and b, whose square lies between 0 and 2p. It's equal to 0 mod p. So it cannot be 0, cannot be 2 times p. It has to be equal to p. Done. It's an amazing application. I mean, a lot of this has come out of nowhere. So this is not an imaginary number, right? So this is a number in, maybe I shouldn't have used the number I. This is the square root of minus 1, mod p. Mod p. Mod p, right? That's the difference. It's not a complex number, it's that would have been strange. That would have been truly strange. But you see, a lot of this has come out of absolutely nowhere, and it's a very simple, in fact, a 5-line proof. Okay. So with that, 6 minutes over time, we will take a break.